This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, let's just start this before that I close the door because that distracts me. Hey. Sorry, what's your name? Moa. Okay. All right. Yeah, I'm Iman Chains, and I'm going to be your lecturer. For those of you who've enrolled, for those of you who haven't and just want to listen in, I will be your entertainer this semester in the area of introduction to, optimization, particularly introduction to optimization. Now, just to get a feel of how many of you have certain backgrounds, because come from different backgrounds, raise your hand if you remember anything from your linear algebra course. So you remember linear algebra. That's very good. That's a good start. So we are going to heavily use everything you learned. And who remembers what the fundamental theorem of calculus was? Okay, brush up on that, because that's the fundamental theorem of calculus. We're going to use that as well. It helps you understand whatever we're going to talk about. We're going to review some of those things today, and let's see how it goes, right? And another question, how many of you feels some terror when I talk about real analysis? So at least you know about it to feel terrified. How many of you know about real analysis? Okay. That's some basic ideas we are going to use throughout the course as well. Again, it really helps you understand what I talk about. Otherwise, it will just be, I tell stories and you will see maths. They don't make sense. I try to explain things from the fundamentals, but at some stage, I rely on you that you go and brush up on your background. Okay? Cool. Now, let's set up the expectations, at least my expectations, right? You will see a lot of theorems and statements and formal definition, etc., etc. I have no expectation that you can reconstruct the proofs and statements in details, but the expectation is that you make sense of them. So you can, if you see a formal proof, you have to be able to understand what is the point of this proof and be able to explain, at least to yourself and your friends and me, what is the point of this particular statement or not. So that's the first thing. It's a dense subject in the sense that I borrow a lot from different areas that you have seen, but probably you've forgotten. So it really helps the understanding if you just go and have a look at your old textbooks, old notes, and really just try to refresh your background, really. Okay. The other thing is that knowing it is good, but at least knowing about it, or mathematical optimization is a great advantage. And it pays off to see it as an investment. And not very appropriate examples that I've heard about these sort of areas. Maybe I have to pause it. I might get into trouble later. Okay, good. The style that I will teach is something I just made up. I call it rigor light. I try to make it rigorous, but I don't get bogged down in minutiae of the background and theory. So I can state a lot of these, for example, just for those of you, I can state a lot of the results in general Hilbert spaces, but I don't care. I talk about real all the time, vector fields. Because the purpose is not to have a super general framework. It's to have a useful framework. So, and really we try to keep it concrete, and we help it to and be guided by abstraction. It's something that is missing from a lot of your undergrad curriculum now is the ability to abstract complicated problems. So in the end of it, so we jump to this, I really hope that you don't treat mathematical optimization as some black magic or a massive hammer that you can go and hit every single nail with the same hammer. That's where abstraction helps. So we have to understand the properties of the problem we want to solve, and then just go and come up with the tool that is appropriate for that particular problem. Okay? It's a quote I really like, and it's really a truism. Roger Fletcher was this famous guy in applied mathematics. And really the observation is mathematical programming, another name for optimization, is a fascinating blend of theory, computation, and heuristic, and rigor. Sometimes we have to marry those abstract ideas with the very concrete concept of a machine that does computation. And how many of you have heard the name Trefethen? Okay, Trefethen is this pioneer in numerical methods. And if you go and look at the LMS page for this course, I've put up a link to, and he has 40 maxims. So and he calls them Trefethen maxims. His argument, one of the arguments that he makes is that while the computers are becoming more powerful, we have to become more careful about how we treat them. So take advantage of that power, because otherwise we are not making any progress anymore. So it's important to think about these things from the beginning. So whenever I talk about stuff, I will try to touch on every single one of these 4 broad topics. I talk about what the theory is, I talk about what are the computational aspects of the particular problem or algorithm we are looking into. What are the heuristics that we can improve it, at least from a practical point of view, and we always want to have some proof of performance. So the main text that I'm going to heavily rely on is Numerical Optimization by Jorge Nosadal and Steve Wright. You can download the ebook from UniMelbourne Library. It's a Springer book. So again, it makes sense to have the textbook. Now another question. How many of you have looked at a textbook in the last month? Maybe. You weren't sure if you looked at it. Oh, okay, good. A textbook is the best source of learning anything you can imagine, because some person has spent years to distill an idea. I mean, a good textbook, that's implied, as one coherent, hopefully coherent tome. So if you don't, you have to pick up the habit of reading textbooks. I assume all of you are postgrad students, PhD, or MPhil students, right? That's the only source that I ever learned anything out of. You go to lectures to get pointers to ideas, to maybe clarify certain things, but in the end of the day, you read it from the primary source. And you read it on your own. The other book that I will use, especially for 2 of the chapters, in 2 of the lectures, is Dimitri Berseka's book, Convex Optimization Algorithms. This is not available, but I'm sure you can download it from Russian websites. And then another book that is just famous, I put it there so that the list is kind of complete, is Convex Optimization by Boyd and Vandenberg. I don't use it much, but you can use it as something to go about and read it, especially on the topic of convex optimization. Now, that's something that we have to talk about, especially with those who have enrolled or planning to enroll formally in this. It's really the idea of assessment. Currently, in the handbook, the assessment is 40% homeworks, 60% final. So I will release homeworks, you will do them, you will get 100 on them, because if you really care about the score, a lot of the solutions are available online. So, and I don't care if you go and copy it. You're grown-ups, you can pick however you want to learn something. So I expect everyone to get that 40% completely. Then there will be a hard enough final exam, which is easy to pass, but it won't be easy to get a good mark. So that's the idea if you are going to go ahead. But if you ask me, I think a better way of learning this subject is through doing a project. Because then you get hands-on experience and you spend some time on it. And I've tried this in different forms. The problem is that it doesn't work as well as I want it to work, because a lot of people don't have the background, so they have to wait until towards the end of the semester, so we cover the lectures, and then they know enough to go and do the project. Now, to be able to do that, I thought about an alternative. We can try to condense all the lectures in the next 3 weeks, and then there are 6 of you who have enrolled in the subject formally. Then from that point on, every Wednesday, the official time for the class, I will spend 30 minutes with each of these students to discuss their project if they want. Of course, people who are just auditing this will not have a say in that. So how many of you have enrolled or planning to enroll in this subject? Rushi. More, you have enrolled as well, right? No. Huh? Yeah, but if I asked who have enrolled, you didn't respond. So, okay. So you are the only ones who will have a say. So either we stick to the current schedule, have 3-hour lectures on Wednesdays, maybe break it up in 2 sessions. I don't know. We have to discuss that, and then have an exam in the end, or we will have lectures, 2 hours lectures every day for the next 3 weeks, and then have a big chunk of time dedicated to the project. Who is in favor of the project? 1, 2. So I assume 1. Who else other than Rushi was enrolled in the subject? You too. So it's an impasse. So there are 4 of you, right? The LMS shows more. Well, you didn't tell me. So do you want more? Do you want project or not? Yes? Okay. So let us, because the other thing is that to be able to change the handbook, change the assessment criteria in the handbook, we need unanimous agreements. So if you guys want to do the exam, it is easier for me in reality, because there are 6 of you. Marking 6 exams is heaps easier than reading 6 reports and talk to you throughout the semester. But I think it is the worst learning outcome. But whatever. By the end of tomorrow, and it's very odd because other people who formally enrolled in are not here. Yeah. By the end of tomorrow, if you still want to do the exam, that's how we go ahead with it. We do the exam. Okay. All right. So the subject outline, the topics that we will cover are these. First, I will talk about, in the next lecture, I'll talk about line search methods, things that are similar to Newton's method, gradient descent, etc., etc. Then we will discuss quasi-Newton methods. Particularly, we focus on one family of methods that is known as BFGS. Then in the third lecture, we will just have a bit of an excursion to convex functions, convex sets, convex optimization, what it means when we talk about convex optimization. Then we will spend some time on least squares, really just try to relate probably the most famous application of numerical optimization to solving least squares problem. Then we'll talk about derivative-free optimization, and then from that point on, we will focus on constraint optimization, talk about the theory behind constraint optimization. Then we talk about, we skip that, we talk about duality, subgradient methods, and dual decomposition for distributed optimization solutions. Then we'll talk about gradient projection. And the last two lectures here would be penalty and augmented methods, and then interior point method. Then we will have a look at some other applications of optimization theory. So this is the broad outline of the semester, and the lectures they follow the same outline. All of them are on LMS as well. Now, again, I have to be clear about this. That's why I keep repeating myself. What this subject is not about, I don't teach you how to use a particular software package. You can, for your assignments or whatever you are doing, you can go and pick whatever package you want, but you have to be able to use it to read that manual. To be able to understand what method to use in that package, you can rely on what you learn in this class. I will not give you a silver bullet to kill all your enemies, because this is not the point of it. You will not get a hammer to hit every nail. You have to think. Now, what this subject is about, hopefully you will build a foundation that allows you to choose an appropriate method for a particular problem. That's, if we satisfy this criterion, I would be very happy. Based on that, you will learn what type of methods are suitable for what type of problems. Again, to be able to choose wisely. And you will understand that some numerical properties of these methods. So again, inform your decisions. And hopefully you will be able to see through the hype. Because these sort of hypes come in waves. Every few years, we talk about how optimization is awesome, or we give it different names. We call it machine learning sometimes, we call it reinforcement learning sometimes, we call it neural network sometimes. All of them live in the same domain. They don't solve all our problems. We have to be careful. So if you thought, I'm going to teach you how to use a package, this is definitely not a good subject for you. It would be painful. Okay. So now we are going to get into the lecture proper after all this background. Any questions? Okay, good. So the outline for today's lecture. I will start with some history to be able to tell a story. I talk about what is a general optimization problem. We briefly go through different optimization problems and what is a generic iterative method to solve this optimization problem. We start with our first introduction to some complexity bounds for solving a particular problem. And then we briefly will review some backgrounds that are needed to construct and analyze optimization algorithms. Then we will see our first definition of a minimum or different types of minima and some basic theorems for identifying them. So that's where the party starts. So hopefully by the end of this lecture, you will be able to identify an optimization problem when you see one. Some of you probably can do it already. And then you appreciate the ingredients of a general iterative scheme for solving optimization problems. So what is a generic method? What are the components that are needed to put together a method? And then some basic understanding of the tools needed to analyze optimization algorithms. And hopefully it will raise some flags for some of you regarding the things that you have forgotten. So you go and read them. It is surprising how many times I say this and how many of the students don't do it. Pick up a linear algebra book that you like and just refresh your memory if I start saying things that don't make sense to you. Pick up a real analysis book and just look at it for some time just to familiarize yourself with some of the definitions. Again, I will mention some of them, but not all. By the end of today, you will see the different types of minima as well. And then recognize conditions for when we find a minimum and what is a minimum. Okay. How many of you have done a subject or a course in dynamics? Okay. So an example of optimization in nature is the nature itself. You can think of the physical world as a solver for optimization problems. Now, can someone explain, based on your background in dynamics, why I can make a statement like that? Do you remember Lagrangian, Hamiltonian?
It's all about minimizing the action?
Yes. So we try to take a least action path, and what least is to minimize something. So whenever I drop a boulder down a valley, it goes to the bottom because it's trying to minimize some function. Okay? In business, people apply it to portfolio management. We might see some applications there throughout the subject. And then resource allocation was one of the heavily studied problems in business and later on in comms networks and power systems. And science, it was used since probably early 1800s, late 1700s, when people started fitting curves to data. And nearly any engineering problem that you can think of can be written as an optimization problem. It doesn't mean we can solve all of them, but we can write them as optimization problems. If I want to move a robot from one point to another point, I can say I want to minimize the time that it takes for it to travel there. I want to minimize the error in the end that I end up at my destination. I want to maximize my distance to a bunch of obstacles around me. That's just the robotics application. But it can be applied to any sort of engineering problem as well. So is there anyone who can think of an interesting problem that they've seen that can be formulated as an optimization problem here? Now, one other thing. All of you who decided to sit in this room, you agreed a sort of a covenant with me to participate. That's why I ask your name, right? So I'm going to ask your name. If either you do it voluntarily or just go through every single one of you. It's very uncomfortable, but after some time you get used to it. It becomes easier. So Ethan, can you think of, do you know any example of an optimization problem that you've seen? Sure. That's an idea of a curve fitting idea again. we've observed a bunch of input and output pairs. I want to construct a model that now try to mimic those outputs. And I want to minimize my error, in a sense, some error. You'll spend a lot of time in lecture 5, I think, on that problem. Okay, so let's go next. The oldest example of optimization that I could find is stated in 19 before Common Era in Virgil's Aeneid. It was the story of Queen Dido. I think Dido was an exile of Troy. I'm not sure. Well, the story goes like this. So they were kicked out of their home. They had to find a place for a new settlement. And the idea was that she went to the market and bought and was negotiating some land settlement, and they told her, okay, they thought they were being funny, and they gave her a bull hide and said, okay, you can have as much land as you can, but you have to encircle it with this bull hide. So then that's the question, is that she wanted to maximize the area, the overall area, while making sure the perimeter of the area is constant. Okay? So that was the problem that she had to find. So really the formal definition of the problem is to find a figure, find the shape of the city, bounded by a line which has the maximum area for a given fixed perimeter. The answer is a semicircle if we bound it one side to the sea. But these sort of problems don't they don't fall into the family of problems we investigate in this subject. They belong to, there are infinite dimensional problems, and people who've studied calculus of variation study these sort of problems. But in the end, they are optimization problems. We can try to approximate them with the methods we talk about in this subject, but they belong somewhere else. And then in the 60s, as I said, these sort of hypes come in different waves. In the 60s, people had, 8-bit computers. It was amazing. So they thought, okay, now we've been studying these sort of optimization problems. With these super fast computers, we can solve them, solve everything we want. So there is a saying that says, and every year I intend to go and look up who said this, but I keep forgetting it until next year. I see it in the first lecture, so I have to fix that. But anyways, I read it in one of the books I was reading. It's really, nonlinear optimization is very important and promising application theory. It covers almost all needs of operational research and numerical analysis. Grant, I love this. It fused with optimism of the 60s. But then a few years later, a few decades later, Nesterov, which is probably one of the most influential figures in this whole theory area, in the introduction to his book, starts with this, to really dampen all this. In general, the optimization problems are unsolvable. And I think that's important to remember as well. And again, he goes on and says in our, it's really a regal hour, this statement, which is usually missed in standard optimization courses, is very important for understanding the entire theory, its past and its future. So what we try to do is to identify what problems are solvable and how to solve them in a meaningful way. In general, these problems are unsolvable unless we have super-duper quantum computers. Maybe they happen, I don't know. Even then, we will have problems, but that's a topic for another time. So really, again, we have to focus on what can be solved and what can be done about these sort of problems. Something that is important is that if I conjure a method applied to a problem, and then it works for that problem, it doesn't mean that method will work for anything else. So we need to come up with some properties of methods in conjunction with problems that together make sense. So these are the three pillars that we will look into again. Again, I've been pushing this in different languages over the last 11 slides. Again, we will talk about conditions under which a particular solution is valid. So a particular method is going to solve the problem. They fall in the category of convergence proofs. So whenever a method converges to a particular solution that we are interested in. Then we look into the computational aspects of the solution. I can have a great method, but takes the method that gives me the exact solution to a problem, but it takes the lifespan of the universe to give me that solution. That's useless. To be able to do that, now you have to understand the numerical properties of that method. And then we have to be able to characterize how the performance of a particular method degrades as we move away from the idealized situations that we assumed when we analyzed it. Because, okay, let me ask you a question. When we come up with a method, we make a bunch of assumptions. Let's say we show that it works the way we want it. But why should I care about this graceful degradation of the property? So some of those assumptions are not going to be satisfied in reality. I don't want my method to suddenly fall apart. Can someone give me a concrete example of why we need the last property when we want to solve a real-world optimization problem?
If you're using some kind of iterative solution method, if your step size is too big, for example,
No, you're jumping way ahead. It's something very fundamental, and think about computing. It is related to what you're saying, but it's much more basic than that.
computation is a graduated thing, not continuous.
Close. Do you want to?
Is that rounding error? From that point of view, right?
Yes. So that's something that always exists. We do our analysis most of the time in Rn. But when we implement it on a machine, what number system do we use? No, binary is representation of a number system. We use floating point number system that uses floating points or a fixed point in implementation of methods. In the end, we have rounding errors. We cannot have infinite precision. That automatically introduces error. Okay? So we need this because it's a very practical issue. But we have to be sure that we don't hang on the edge of some precipice when we develop that method, so that the moment that we pushed one side, it just falls apart. Okay, so that's a general optimization problem there. Now I'm going to switch to this. Okay. All right. So this object there is known as the objective function, or the performance index, or the cost function. Sometimes we want to minimize it, sometimes we want to maximize it. Again, the name that we give to that object really doesn't matter. Different areas, we can call it different things. You have to understand why we put it there. It's something that we want to either maximize or minimize. Then there is this other object. In this example, we called it x, but it can be any other alphabet. It can be, I can replace x with an apple, and the definitions follow. So we are not married to the notation. Again, we have to look at it from an abstract point of view. I just gave it a name. I could have given it any other name. But for consistency, we are going to stick to these sort of variables. It's called the decision variable. If you go and look into the older literature, they used to call it control. And that's where a lot of these areas really converge in the past. Then there is a set membership that we belong to some calligraphic set X. Now it's called the feasible set. It can be continuous or discrete. So really what the meaning of the statement on the top of this page is we want to minimize or maximize. Here I just put minimize. We want to minimize some function fx. So I want to find the value of some decision variable x that returns the smallest value for fx, but I want to limit x to belong to some set calligraphic x. So of all the elements in calligraphic x, I want to find the one that minimizes fx. Now that set calligraphic x, as I said, it can be anything. It can be continuous or discrete. It can be sometimes a mix of both, either of these two. So how many of you remember what it means, what this means? Yeah, L2 no. What is another name for L2 no? Okay, how many of you doesn't know what an L2 norm is? Okay. Elena, can you tell me what an L2 norm is? Okay. How many of you doesn't know? Please raise your hand if you don't know what L2 norm is. You've already done it. Okay. So you don't know as well? You don't know? I'm trying to remember. Maybe I never asked your name. Sorry, what's your name? Ching Chang. I never asked your name. Can you tell me what L2 norm is?
Square of x.
Okay. It's not quite that. If x is a vector, what is this? Can you tell me the definition of this? Yes, L2 norm is another name for this Euclidean distance. So do you know what Euclidean distance is?
The length.
So how do I write it using algebra?
Square root of square, the sum of square.
Now, I can have P here. Can someone tell me what is the definition of an LP norm?
One over sum square.
It is this.
Sum of x to the power of p to all to
The absolute value of sum of x to the power P then the pth root. Yeah. This absolute value is important because if p is odd, then you might end up with the strange things. Definition of norm doesn't hold anymore. So that's the first thing that we are going to see. Go and look up, probably on your second lecture of any linear algebra subject you've done, there was a topic on norms. Go and look at it. Because that's how we are going to use those tools to formulate problems and measure performances. Okay. Now that we fixed that, can you tell me what this set tries to characterize? Can anyone tell me that? Okay, it's getting better. Good, but still, what about the hypersphere? Sure. Surface? Okay. The interior of a unit hypersphere. So the hypersphere on a plane is a circle. In three-dimensional space is a sphere. In high-dimensional space it's something that I can't imagine, but it exists. So it's the interior as well as the surface of a hypersphere with radius 1 in that example. If you go back to your high school, that's how, in 2D at least, that's how probably you used to define circles. Okay. Again, when we talk about convex sets, we try to go through these a bit further as well. This other object is A, again, X belongs to Rn, and A is some matrix with appropriate dimensions, B is some vector with appropriate dimensions. Can someone tell me what sort of set this other constraint set characterizes? Yik, do you know?
Sorry.
Do you know what type of set is characterized by an equation like that?
Not that I'm aware of.
Okay. Nice, right? You don't need to be sorry.
I think it's unit plan and one line here, and all things are less than b.
Okay. It's kind of close in one dimension. That's what you're saying. Each line, each row of that matrix, along with the corresponding scalar in vector B, corresponds to a hyperplane, and then that direction determines one side or another side of the hyperplane. So it's really an intersection of a bunch of half spaces. It looks like this. So a set like this can be characterized by a set of affine inequalities. The last set is pretty simple. It is just a bunch of discrete values. 1, 2, 3, a bunch of integers. Okay? Okay. So these are the objects that we work with. A cost function, a constraint set, and a decision variable. Okay. Throughout this subject, I will exclusively write optimization problems, nearly exclusively write optimization problems as minimization problems. And I'm going to make a not very bold statement. I'm saying, from the perspective of analysis and design, I can write all your problems as minimization problems. Why can I say something like that? Yes. If I'm maximizing something, it's the same as minimizing minus of that something. So it doesn't really matter if I'm doing maximization, minimization. Okay? Is it clear to everyone? Someone could have said, yeah, I can write maximizing f as minimizing 1 over f. That kind of similar thing as well. But I would say that's a bad idea. And we will see why that's a bad idea, because sticking a minus behind an object doesn't change its topological properties. Putting in the denominator of something does. So we don't want to mess things too much. All right. Yeah.
The amount of visible sets
Yeah.
to be finite dimensional.
In this subject, I talk about finite dimensional objects. Everything is finite dimensional. F is finite dimensional. X is finite dimensional. I mean, F is really just a scalar. X is finite dimensional, and the set corresponding set is finite dimensional. It doesn't mean it is it doesn't mean it is finite. It can be infinite, but the dimensions are finite. So we don't look at function spaces, for instance. So now if we now focus on a continuous optimization problem, so the constraint set is just a bunch of, the constraint set is continuous, we can write the problem slightly differently. We can say, okay, we are minimizing fx. Now, subject to two types of constraints. The first set of constraints are called them Ci of x equal to 0. It means my decision variable should satisfy that equality constraints. And they can be more than one, so I put all of them in a set that I call calligraphic E. Is the indices of equality constraint set. And then I want my decision variable to satisfy the inequality constraint as well. Ci of x larger than 0. And I put all those indices in set calligraphic I. Okay? The standing assumption, unless stated otherwise, is everything is differentiable, so I can take derivatives. All these functions are differentiable. Again, there will be situations that it's not the case, and we will briefly study them as well, but as a standing assumption, let's make that assumption. It makes our lives easier. Now, I can put this form into this form. How do I do it? Didi, can you help me?
Sorry, can you show the previous?
Both of the slides are here.
Oh, yeah. Sorry, I'm not sure how to. I'm sorry.
Rushi, can you put this problem into that form?
Yes,
No, I'm going to ask her now.
I guess X went to the solution of the equation.
Okay, close-ish enough, but you have to be a bit more careful. When you say x belongs to the solutions of those functions, how do you define, what do you mean by solutions? I can define a set. I say, okay, let's define a set. My set is, sorry, calligraphic x. And just to annoy you, I'm going to use another variable here. I'm going to put z, because I can put whatever variable I want anywhere I want, as long as I'm consistent. So all the z's that satisfy all the equality constraints, and that's logical satisfy that inequality for all the inequality constraints. Does everyone know what this symbol means? For all. This is and you see, I was hoisted by my own petard, and no one cut me. So. Okay, so that's how I can define a solution set in the way that Rushi explained it. I can call it a feasible set as well. I had a German lecturer that really was very personal with maths, and he said, I can name my children whatever I want. So these objects, you can treat them as your children, you can name them whatever you want. Now here we choose to call them a feasible set. As long as I define it, I can call it whatever. I can call it apple set. It would be valid as long as I always refer to it as the apple set. Okay? So it's the set of all the points that satisfy these relationships. Okay, so we can write it as that general form of the problem. So a bunch of you are in mechanical engineering. 2 of you are in biomed. So I don't know about you're mechanical? Biomed as well? Electrical, what area? Oh, you're doing the 5-year master? Yeah, okay. Electrical PhD or masters? Again, the same, yeah? What area are you in? Computer science? Master as well? Okay. All right. Now, what was the point of my question? I forgot. You're in electrical. I've seen you in the corridor. Who do you work with? Okay. So probably you will appreciate this. Maybe. A common problem in comms networks is network utility maximization problem. A simple setup is like this. I have a bunch of sources. You can think of them as servers for a content. And in this problem, you assume sources are sources and sinks as well. So they are servers, and they want to get information from other sources. There are multiple paths between sources, different pairs of sources as well, that they go through routers, and we have communication links between these routers. Okay? In a comms network, or any network really, I mean, I can write a similar problem, treat it as a power network. These links have finite capacity. So I can put infinite amount of flow through them. Okay? You look very concerned. Elena, can you tell me what is the source of your...
No, I'm just thinking.
Oh, you're thinking. Sorry. Now we are going to simplify the problem. We are going to assume the flow that goes from source 1 to source 3 will travel through link 1 and link 3. The traffic that flows from source 3 to source 2 will travel through link 3, link 1, and link 2. And then the traffic that flows from source 2 to source 1 will go through L4, and L1 goes to S1. Now, if I want to enforce the capacity constraints, what does it really mean? It means, for instance, the sum total of flow of this dotted flow And the solid line flow that goes through this link should be less than the capacity of link 3, right? So I can write it down like this. I can go write it here. Okay. So I should say x3 plus x1 should be less than, we use C to denote the capacity of a particular link, should be less than capacity of link 3. So this is this link. What can I write about this link? Exactly, because all the flows will go through that link. Similarly, here only is x3. Okay? Is it clear so far? So we just are writing constraints for these capacities. I can go and put together a routing table and really concatenate all these constraints into one vector form. Because if I go back here, I can put all my decision variables in on top of each other. I call it x. And if I want to come up with a compact way of writing this constraint, it should be now so C is the concatenation of C1 to C4. Now, how do I construct R? R should give me all these different constraints, right? So the first line of it, for example, should be that. So R, the first line would be 1, 1. Let me do exactly this. So this would be my R. Yeah.
I'm a little confused about the general problem statement. Is the goal to find the best routing table?
No, the goal is, I haven't explained the goal yet. I'm just setting up the constraints of the problem first.
Okay, but the routing table is fixed.
For this problem, yes, the routing table is fixed. Yeah, sorry, there's a transpose here. Yep. It's yeah, there's a transpose there. Good point. Because now if I multiply that, it is slightly different. Yeah. So what is that? What is the result of this multiplication? I should modify this. Sorry, my bad. So if I do this, I end up getting. How do I do this? Becomes 1, 0, 1, 0, 1, 0, 0, 1. 0. Right? Sorry. Yes. So if I now multiply, it would be x1 plus 0x2, x3, no x4s. The second one gives me x1, x4, and then I missed one line as well. Yeah, no. x1, x2, x3. You know, like here, we have different versions of this here. That was the mistake, sorry. There are only 3 flows. I was writing it for a different problem. There are 4 links, but there are 3 flows. This one was correct. This is exactly the same thing. Less than 1. Sorry. The second line is x3 less than c2. The third line is x1 plus x3 less than c3, c4, which is that. So now we have the capacity constraints. Now we have to think of what is the meaning of the cost here. So in comms networks, logarithm of a particular flow is a proxy for the content of information in that flow. So we want, if the utility of a network is defined as the sum of the logarithms of all the flow that I can put in that network. General ideas can be applied to any sort of networks as well. So it's just one example of a network utility optimization problem. So we have a network, we want to pump as much flow as possible in it without violating the constraints of the links. Now where are we? Okay. Then there is this other problem. It's a basic, simple problem, but it looks a bit different. I want to minimize this quadratic cost subject to these 2 constraints. The cost and the constraints, they are in 2 dimensions and they have a simple geometric interpretation. So if I write it, this is that curve is x1 squared minus x2. And this line is x1 plus x2 equal to 2. Going back to this, what is this object characterizing? Correct. It is characterizing a circle. So if I write it like this, cool. What is this? It's a circle centered at where? And 0. And with what radius? Radius of, right? So yeah, it's simple geometric interpretation. It looks like this. So this is 1.5. So I can write it as okay. The constraint set said x1 squared minus x2 should be less than 0. If I have a quadratic curve like that and a constraint like that, is it below the curve? Are we characterizing the set here or here? Can someone is above the curve, right? It's here. If I have a I mean, it's really just a line. If I have a line and I'm interested in all the points that satisfy this relationship, this would be above the line as well. So we are interested in the constraint set is all the points in the intersection of these two sets. Now I want to find a point in that set that minimizes this object. This object is the radius of some circle centered at point 1.5 and 0, right? So if I pick a very small circle like this, its radius is small, but what goes wrong? It doesn't intersect with the set of the feasible solutions. So I have to increase that radius until I can find a point in that intersection. Now, in this scenario, it happens to be exactly this corner. So now we have a solution. We solved our first optimization problem in this subject. Okay, while we really relied on a lot of geometry, what is the shortcoming of a method like this? We don't have that geometric intuition for large-scale problems. So it's not really useful to solve general problems. So we have to come up with a different idea. Again, another, like I said, call it not so easy, but it's a basic problem. I can have an ugly cost function and some nice constraint sets, but as long as the dimensions are low, I can really just plot it and find a solution here. Ta-da! But I cannot do a similar thing for large-scale problems again. And we're going to see an example very briefly. So really, we want to be able to answer a simple question. How can we determine certain points minimize the cost? And we might end up having with many local minima and only one global minimum. So we have to be able to first characterize what these objects really mean as well. Otherwise, they are just names. It's another problem. It has historical values in the Battle of Britain, but you can skip this. Now, let's have a break for 5 minutes. We continue in 5. Because we won't survive 3 hours of this. I won't. All right. So let's look at different categories of problems, optimization problems. There are different ways that we can put them in different families. The first is constrained versus unconstrained problem. So we can talk about integer programs, mixed integer programs, continuous optimization, but in this sort of partitioning of, I looked at constraint problems versus unconstrained problems. We can think about global optimization, local optimization. What we really mean by that is, are we after finding global solutions or just some local solution to a particular problem? Global problems, to be able to solve that, a lot of problems globally, we need to solve a whole heap of local problems, and they are often inefficient. There's another sort of partitioning of the problems into stochastic versus deterministic problems. And again, in that setup, we usually try to translate a particular stochastic problem into a deterministic scenario and then try to say, our results now come with a quantifier, usually with some probabilistic guarantees. Families of chance constraint problems, robust optimization problems fall in this sort of worldview. And then we can partition the problems into convex problems and non-convex problems. And this is, in the words of Tyrell Rockefeller, is really the watershed moment in really a lot of function analysis. And optimization theory is the line between convexity and non-convexity, not linearity and non-linearity. Just as a rule of thumb, convex problems are easy to solve. Non-convex problems are not easy to solve. But easy is we have to quantify it and we have to be careful about it. What we really mean is that we can construct problems. We can construct solutions that come with some guarantees, but it doesn't mean they are necessarily solvable using standard computing devices. We have to, again, be careful. And when we say non-convex problems are not easy, what we really mean is we cannot have the sort of guarantees that we like. We are going to see these things in more details in the coming lectures. All right. Now, a bunch of terminology that allows us to talk about problems and talk about different methods is really the idea of an oracle. In general, any method that we use to solve an optimization problem, we apply to some problem P that belongs to class C. So that class C can be any of the things that I talked earlier, convex, non-convex, integer, non-integer, anyways, depending however we put them in different classes. And each problem comes with an oracle. This oracle answers questions that the method asks. We have two assumptions on these oracles throughout the semester. One is, we call it black box assumptions. What they really mean is this. The only information available for the method comes out of the oracle. So the oracle provides all the information that the method can use. And then the oracle is local. What it really means is if you're asking about, for example, some properties of the problem at point X, if we perturb the query point to X plus delta X, the answer of the oracle is not going to change too much. It's an idea of, we can write it as pose it as a continuity property for the oracle. They are just technical assumptions. It's fine not to worry about it. There are different types of oracles, zeroth order, first order, second order. Zeroth order oracles really just return the value of the cost function at a given point. First order return the value and the gradient of the cost function. Second order oracles return the value, the gradient, and the Hessian of the cost function, and potentially the constraint functions as well. But that's the sort of idea. So we can design methods that use these three different types of information. If we really are keen, we can have higher order oracles. but the use of higher order information really hasn't been proven to be very useful in solving optimization problems. You can construct higher order methods, but they usually don't have. It's in the other way, it's not worth the effort for the minimal gain that we get for using third order derivatives, for instance. So we focus on these three types of oracles mainly. Now, this is a general iterative optimization method. So it's a pseudocode with a bunch of commentary. So whatever method that we are going to use, we start with an initial guess, x naught. And we start with some tolerance, accuracy, precision, however you want to call it, that we want to put on the solution that we get. I use epsilon for it. Then we set up a counter that counts the number of steps in our method. And we set up a set that really denotes the amount of information that is available to the method at any given time k. You start from an empty set because initially the method has no access to any information about the problem. And as long as our accuracy / termination condition is not satisfied, that is related to that epsilon that I introduced earlier, we call the oracle at point xk. Now, depending on the type of the oracle will return a bunch of information about the problem. It can return the derivative, it can return the value of the function, it can return the Hessian, etc., etc. And then we just put it next to everything else we knew about the problem. So we construct a history of these queries. And we make this information available to the method. And the method uses that information to come up with the guess at the next step. So we started with some initial guess x naught, and then we keep constructing guesses iteratively. We increase the counter, and we repeat. Hopefully, we've designed the method along with the termination condition in a way so that this loop terminates. And then we end up with an answer. We find the minimum value as well as the minimizer, hopefully. Now, this is a very high-level general scheme. Can someone tell me from this, when we are designing a method to solve an optimization problem, what are the two main elements that we really have to pay attention to when we are designing an algorithm to solve an optimization problem? That's good. Let's assume the solution exists. Yeah. We should design the method. We should really co-design the method and the termination condition together. For example, if my method uses gradient information, I cannot put my termination condition on Hessian values. Right? So it's something that we will see a lot. We have to, the method and the termination condition should be picked together. They should be consistent and they should make sense to be able to have a solution that has the properties that we like. In the computer science literature, is to have the liveness property. So it terminates. All right? An overview of optimization methods is the global optimization. The aim is to find the global solution to the problem. We can look at continuous functions, and there are different oracles that are used. The aim is to converge to the global minimum. From a theoretical point of view, the game is too short. We always lose. And I will show you a simple example why I make a statement like that. Problem sizes, they are not really scalable unless we throw a lot of computing. I mean, they are not, we cannot scale them nicely. We have to throw a lot of computing power at them. and they behave in a way that they are not predictable usually, these problems. They start with, the idea started in the 50s. Again, it's my personal opinion. I think every now and then with each leap in the computing power, people get super excited about these methods, then they realize they don't work. So we are at the end of the fourth wave of these sort of methods again. Because I was in a conference a couple of months ago, and now all the autonomous vehicle companies are saying, oh, we are not interested in end-to-end neural networks anymore because we don't know how they work. It's at the end of another, until the next 10 years, people say, oh, that's the solution to everything. And I warn you against all these sort of panacea sort preachers. You have to be careful when you pick up solutions. They started in the 50s, then they died off in mid-60s, and then in mid-70s they started again. They died off in mid-80s after a bunch of aircraft crashed. Then they started from mid-90s, ended up late 90s, and again they came back early 2010s, and now the hype is deflating now. But we never know. And then there is nonlinear optimization. The idea is to find the local minimum. Usually we stick to differential functions as well. Differentiable functions, we can deal with non-differentiable ones sometimes. We can have convergence to the local minimum, and we can have fast convergence. We have to be able to quantify it. We are not ready yet. Hopefully by the end of the day we have some tools to quantify that. There are different methods and software, and we can solve them up to thousands of variables, problems with thousands of variables. If you are careful, if we use really the structure of the problem, we can solve larger problems. Again, started in the 50s, peak theoretical contributions were till late 70s. The theory is fairly mature now in this area. There are certain bits and pieces of it that people are interested in now, but the general theory is fairly mature. Then in convex optimization problems, because of the structure of the problem, we can use the nonlinear methods, optimization methods, to solve this convex problem, but we end up with a global solution. We are limited to convex sets and functions. We mainly use first-order black box oracles. And we can get different rates of convergence. Usually the methods, the first-order methods, depend on the dimension of the rate that we converge. The solution depends on the dimension of the space. From my perspective, a lot of interesting problems, a lot of practical applications of these methods as well. We can really solve it more than 1,000. We can solve problems in the order of tens of thousands of variables now on a computer like that, and people are interested in the theoretical aspects of it. And then there were the interior point methods, which is a subclass of convex functions. When you say explicit structure, there's a smaller family of problems. They really can solve massive problems, hundreds of thousands of variables, even millions of variables. It's nearly covers the same family of problems. It uses higher order oracles, uses second order oracles, and it solves, as I said, it can solve very large problems, but has shortcomings. I didn't, for example, discuss this. These sort of methods can be implemented on in distributed setups, but these type of methods, the shortcoming is that you cannot have that distributed information exchange structure necessarily. But we talk about these things hopefully later. Now, I said global optimization, the game is too short and we always lose. Now let's see why I can make a statement like that. Let's assume I want to solve the optimization problem given I want to minimize a cost, fx. X is a vector, n-dimensional vector, and I'm looking at all the values of x in that box. So each element varies between 0 and 1. There are n of them. So it's an n-dimensional cube, right? Okay, I want to find the minimum of f inside that n-dimensional cube. If you look at the second item here, how many of you, please raise your hand if you haven't seen a Lipschitz function definition before? So, okay. So no one has, Elena, you've seen it before? Okay, you've heard of it. Okay. Now let's see what it really means. Sorry, I have to think a bit. Intuitively, what it really says is, if I evaluate the function at point x, and then I evaluate the function at some point y, I can write x. Let's just use this. I really can write my y as I can write it like that, right? Y is a point. If, for example, x is here, I travel in direction p, I end up at y. I can always write y as some displacement with respect to x, right? P is y minus x. So what it really means is, if I evaluate the function at point x, then I go and evaluate the function at point y, which is x plus p, the variation in the value of the function is bounded above it, or it is proportional with the distance that I traveled. That's what intuitively it means. Okay? So it really means the variation in the value of the function is not too much if I don't travel too much. It has another interpretation as well. If a function is going to be Lipschitz everywhere, I can have local definition of Lipschitz or global definition of Lipschitz. If it's going to be Lipschitz everywhere, I can write it as this is the same, right? I mean, this is the same relationship. If you see a relationship like this, what can you say about the derivative of function f? Okay. What is the definition of a derivative? Function derivative. Can someone help me? Sorry?
When the quotient analysis, so that's minus y divided by x minus y like this.
Yeah, it's in the limit. As y gets very close to x, just again, we are doing it a bit hand-wavy. There's a better way of defining it, but it's about getting some understanding. If I pick a particular direction, I vary things, gives me the particular directional derivative. This corresponds to the magnitude of the total derivative. So what it really says is the total derivative is bounded by M. It's your calculus and vector calculus, right? hopefully you saw it in a less hand-wavy way that I explained it. So in the end of the day, a Lipschitz condition really says my function doesn't change too much in the vicinity of the points that I evaluated. It doesn't suddenly get unbounded. So it's a nice property to have. We are really enforcing a good behavior in our function. Now, to solve this problem, we are going to propose a method. It's a grid-based method. A lot of people use it without thinking about problems. So let's just put, I have a cube, because that really characterizes a cube in all dimensions between 0 and 1, 0 and 1, 0 and 1, higher dimensions, right? If I now go and uniformly partition this cube into all these grid points, so I partition each dimension to p plus 1 points, there are n dimensions, I end up with p plus 1 to power n different points, right? So I sliced everything, put points everywhere. Sorry, the size of this grid is a design parameter, let's say. We can call it a grid resolution. Then I can go about and evaluate the value of the function in every single point of this grid and find the smallest value f, right? Does it make sense? Anyone has any objection to this method? No one? Good. Now, if I want to have any guarantee on the solution that I get using this method, I have to work a bit, right? I really want to, because I'm evaluating these grids, I want to make sure I am close enough to the solution. Otherwise, any solution is as good as any other solution. Without those sort of certificates of solutions, whatever method I choose is like throwing dots in a dark room. It hits something, but I cannot evaluate the performance of my method, so I have to be able to evaluate it. So that's the statement here. I want to relate my distance from the unknown optimal solution in terms of the properties of the function, in terms of that Lipschitz constant, the dimension, and the number of points. Again, intuitively, the more points I have, you expect to get a better solution, right? But we want to now quantify this. Before going forward, how many of you have seen proofs before? Okay. Those of you who haven't seen proofs, have you seen logical statements, as in P then Q, or P if and only if Q? Okay. So I assume you've seen stuff. Okay, let's go. Let's construct this. You have to interrupt me. If I go through a step, it doesn't make sense. All right. Sorry, what? Yeah, that's exactly, I'm discretizing the space. I'm discretizing the space, I'm evaluating the function at these points, I look at the smallest one. I want to see what is the resolution of my discretization to get the best result, or a result that is close enough to the solution. That's what we are after. But then what happens to the number of points that you have to evaluate? What happens to it? No, they become infinitely large, not infinitesimally large. They become infinitely many points that you have to evaluate your function over. What is the complexity of that? Terrible. Okay, now let's see how I can construct a band like that. Let's assume the unknown solution is x star. Okay? So hopefully, as we are discretizing, we are picking a point that is close to this x star, because eventually this x star solution will be in one of those cubes, little cubes, right? I'm drawing it in 2D because it's hard to draw things in higher dimensions. So particularly, now there exist two grid points, x and y, such that x star falls in between them, right? If I have a cube, I can always find two corners of it that x star falls between those two. So I'm going to define now the x tilde, and I define it like this. I define it as if x star is larger than the half point between the coordinates of x and y, we define x tilde to be the coordinate that is closer to it, y. Otherwise, we pick the other coordinate that's closest to it. So we are defining another grid point there that really is the closest to x star. That's my definition. We are defining it like that. Now, in each, based on this construction, I know along each coordinate, along each direction, the distance between the coordinate of x star and this thing that I just defined is less than 1 over 2p, 2 times p. Why factor 2? Because I define it like this. I pick this guy, which is close. So if I partition this into half, I pick the one that is closest to x star. Okay? So I know this. So the Euclidean distance between x tilde and x star, square of the Euclidean distance, then it becomes like this. I just wrote the definition. Each of these are less than 1 over 2p. So if I square it, becomes n times over 4p squared. So here it's just algebra. It doesn't matter if there were brackets or absolute values. I use this relationship there. Now, if I evaluate the value of function of x tilde, and I know this x tilde belongs to the same grid as well, because that's how I defined it, I can now calculate this. First statement. Why do I know this difference is positive? Because x star is the smallest value of the function, any other value will be larger than the value of function at x star. This would be now, using the Lipschitz relationship, L times this difference. This difference here is just square root of this times L. Right? Now, it might come across as black magic. The black magic part is how to construct this object there. That's the smart bit about this proof. So we constructed a point that allows us to quantify the properties of the solution. But the key point is this. Now, the distance between my solution is always less than L times square root of n over 2p. Okay? So, for a given p, I know if I go and evaluate all the points, I get this sort of error. I can flip this question the other way as well. If I want to get some error, like epsilon, how many points do I need? I want to get a solution that I know is in the epsilon neighborhood of the optimal solution. So let's go back here. If you just crank the handle of algebra using the previous result, you will see you need those many points. And if you just look at it, the only real difference is epsilon 1 to the denominator of that ratio. So I need those many points to be able to make sure I am in the epsilon neighborhood of the solution. Okay? Again, it agrees with our intuition. If we want to get an accurate result, we have to pay a price. The price is in the number of discretization points. How many points do we need to evaluate the function at? So really, that's how this is done. Even we can find a better bound dropping the constant, but that will not solve our problem. Now let's look at a very benign, simple problem. Imagine my Lipschitz constant is 5, some number, and I'm looking at an n-dimensional problem, 10 variables. I want to be within 0.01 accuracy of the solution. We need to validate these many functions. Now, even if I assume my function validation take one flop, which is a very generous assumption on our computing power, on my MacBook Pro, it takes 3 million years. If I go and use Roadrunner in Los Alamos, it takes 273 years. It's the fastest computer now. So that's why I mean, if I want to solve a problem using this sort of algorithm that try to find a global solution, if I want to be able to say anything about my solution, the price to pay is massive if we are not careful. Someone might say, okay, why do I need to have that certificate? But then the answer is, then what is the point? Flip a coin, pick any solution is as good as any other. If you don't care about certificates that look like that. The certificate of accuracy of the solution. Without those, if you really have a belief that why do I care about the properties of my solution, this subject is probably the wrong subject for you, because that's the only thing we talk about. We talk about when our solutions make sense, and what do we mean by it making sense. It's about that. We want to get a solution that is within the neighborhood of the real solution, or however we define that. Okay? Now, what is the necessary background to make sense of the results that we talk about and really to appreciate what we do? Short answer is your undergrad maths. That includes linear algebra and your calculus. And some of you probably have done a version of real analysis. Some of you have done it in engineering maths, but you have seen sequences before in some way or another. So we need these tools to be able to say meaningful stuff. Specifically, I'm going to talk about sequences, convergence and its rate, and very basic topology, really continuity and open sets and closed sets. And then we use this to construct minima, definitions of minima, and then some basic theorems to show their existence. Okay, sequences. If you have a sequence, so you can think of it, if I have a bunch of numbers, okay, they are generated by something. We say they converge to some point x if I can find an index in the sequence such that any point, any index larger than particular index, the point is close to that, the point that we are converging to. So really I can chop part of the sequence from that point on, everything is close to something. That's one way to think about it. Then we can define the idea of a subsequence is I'm given a bunch of numbers, possibly infinitely many of these numbers. I pick a bunch of them, a sub-bunch of them, it becomes a subsequence. They can be again infinitely many or finitely many, it's a subsequence. So these are the two starting points. Then we have a definition of an accumulation point or a limit point. I need this, otherwise we just go through. So the key statement is here. We call x bar a limit point or an accumulation point for some sequence xk if I can find an infinite subsequence out of these xk's such that that particular subsequence converges to x bar. So I have a bunch of numbers. They can be all over the place. There are by construction infinitely many of them. If I can find an infinite subset of these numbers that they convert somewhere, we say that point that we are the subsequence converges to is a limit point or an accumulation point. And an example just to visualize this is I need another color. So imagine this is my sequence. This is the label is k, the time, the index. That's the value of the. So I'm cheating. So this clearly, I mean, based on definitions, if you figure it out, let's say it converges to 0. The black sequence. And we assume it's infinitely many of them. They keep going. They get closer and closer to 0. So now let's populate all sort of other points around it. Infinitely many of the other ones. The sequence in overall, it doesn't converge, but it has a subsequence that converges. The limit point of that subsequence is a limit point of the overall sequence as well. We call it a sequence converging if and only if it has exactly one limit point. What does if and only if mean?
Bidirectional, so one implies the other. Both either can imply the other.
Yeah. So it means a subsequence converges if it has exactly one limit point, and if it has only one limit point, it converges. Okay? This is a pitfall for many people who are not comfortable with the ideas of necessity and sufficiency. All right. we have a useful definition, a Cauchy sequence. We call the sequence Cauchy if after a certain time, a certain index, all the points in that sequence end up being close to each other. They bunch up together. It's called the Cauchy sequence. Every sequence that converges is a Cauchy sequence. The converse is true for Rn, but in other spaces it's not true. But again, we are in Rn, so we can use these sort of tests to show convergence sometimes. If you're in a complete metric space, the converse is true. Rn is a complete metric space, if you like that. We can have different definitions for scalar sequences xk. We call it bounded above or similarly below. If we can find an upper bound or a lower bound that everything is either less than that upper bound or everything is larger than lower bound. Again, it's a very intuitive definition. I'm trying. So if I have a sequence that looks like this, if I can bound it from above, it's bounded from above. If I can bound it from below, it is bounded from below. And I can call these things upper bounds and lower bounds. We call a sequence non-decreasing or non-increasing. In the terms of non-decreasing one, if the next point in the sequence is larger than or equal to the previous point in the sequence. So it looks like this. So it's a non-decreasing sequence. If a non-decreasing and bounded above sequence is, if a sequence is non-decreasing and bounded above, so for example, this scenario, then it definitely converges. It doesn't mean that it converges to that particular bound, but it will converge somewhere. Because I can have multiple bounds, I don't know. The same thing applies to a decreasing sequence, which is bounded below. For sequences, we can define the supremum or the infimum. The color coding is wrong. It should have been orange. Sorry. Which is really the smallest or the largest real number that we can bound it. So it's the tightest bounds that we can find of the infimum and supremum of a sequence. We can construct the sequence of suprema and infima of a given sequence using this sort of definition. So I can look at I can try to find the largest thing so far or smallest thing so in the future to be able to define these bounding sequences. These two sequences have nice properties. The upper bound is not increasing, the lower bound is not decreasing. Again, we can now talk about different properties of them. For example, in this scenario as well, just to work out, if I go and plot it, for all the odd numbers, okay, for even numbers, I start from 0, let's say. The value is 1. At 1, the value is 1. At 2, the value is 0.5. At 3, the value is 1. At 4, the value is 0.25. So it is 1, 0.5, 0.25. At 5, it is 1 again.
Could you go move it up?
Sorry. We are 8. Well, 6, I don't know, whatever. It is, the next one is 1.25, etc., etc. So there we have a sequence, the lower bound, the lim inf converges to 0, and the lim sup remains 1 throughout. All right. Now, why can someone tell me why we care about sequences when we talk about optimization algorithms?
Tolerance. So we need to converge your tolerance.
Yeah, because this language allows us to talk about how the error of the algorithm behaves. Because every single time it spits out a guess, we want to be able to show that this guess is getting close to the solution or not. That's why. Now, the sequence that we're constructing can be just the distance between xk and x star. It can be the distance between f star and fxk. It can be any of these things. But in the end of the day, we want to show this over the sequence generated by the algorithm behaves in a particular way. You can see there's the error sequence coming out of the algorithm. And when we are setting those tolerances in the method, it really is like going back to the definition of convergence. You're setting up that neighborhood that we want to end up in as k becomes larger and larger. We want to make sure that we can terminate the algorithm. Now we can talk about something called the rate of convergence. Because now something can converge to a point, but we have to be able to objectively compare the performance of different methods. Some methods might be faster than other methods, but what does it mean? We need a metric that allows us to compare performances. That's why we have these definitions of convergence rates. Example is, we start with Q linear convergence. Q stands for quotient. Let's assume that of a sequence converges to x star. So we spent a lot of time showing that something converges to some limit point, x star. We call the family of the behavior of the convergence Q linear if we can show this ratio is less than r and r is less than 1. So what does it mean? When r is less than 1, what does it mean?
xk plus 1 is closer to x star than xk.
Yes, because I can move this thing there, say, okay, xk plus 1 minus x star is less than by this much. R is less than 1, so right? Rob, what is
Doesn't R have to be less than 1 if it converges at all?
Good question. If it's going to, it can converge. How to explain this? How do I do? Convergence is the behavior of the sequence in the limit. it can do whatever it wants, because I say k is sufficiently large. It can behave whatever it wants before this k being sufficiently large. But after a certain slice of time, it should behave in this particular way. So if it is going to converge quickly, linearly, r should be less than 1. But I can construct something else. Give me 2 slides. I'll show you an example. This is the same definition as here, strictly less than 1, and we write it in terms of lim sup. Now, there is something that we have to be careful. This factor potentially plays an important role. As I said, Q stands for the quotient. Jesus. What do you do? Anyways, let's look at these 2 sequences. We know both of them will converge to 0 because there are a bunch of numbers less than 1 to power k. Become smaller, 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 smaller. If I start from the same starting point 1, so x naught 1, so really k equal to 0 for both of them, I just evaluate it. After 10 steps, x will take a value like that, and z will be there. Even though both of them belong to the same family of converging sequences, the practical implication of that constant is massive. So even if I have, let's say, algorithms that both of them converge and both of them converge linearly, which is the gold standard of a lot of these algorithms, this factor will end up playing a very important practical role. So the aim is to come up with methods with the smallest factor as possible. All right. So then there is this other, just before going forward as well, it hopefully helps answering Rob's question a bit too, is this. Let's go back here. Let's define, call Ek as xk minus x star magnitude. If I write this setup, it means Ek plus 1 over Ek is less than r. And now let's assume this starts from some point k. I shift time to be at time k0, just for simplicity. So I know E1 is less than r E0. Then E2 will be less than r E1 will be less than r squared E0. Right? I put everything, so I can say Ek is less than r to power k E0. Right? Do we agree with what I did there? Clear for everyone what I did? We just did algebra. Now, in different communities, these sort of convergences are called with different names. In numerical optimization, they call it Q linear. In a system and dynamics point of view, it has a different meaning. We call it exponentially converging. So again, same concept, different names in different communities. The reason that they call it linear in numerical optimization is because you feel like it as per iteration there is a linear relationship between the errors. The reason that in dynamical systems we call it exponential converging systems is because the exponential form there. They are the same sort of behaviors. Anyhow, just something else. Now we are here. We can have faster rates of convergence, which imaginatively we call them superlinear convergence. This is, again, we start with a converging sequence, and we say it is superlinearly converging if that ratio in the end goes to 0. So it's faster than linear, it's superlinear. We can, in the family of superlinear convergence, converging sequences, we can have different versions of it. We can have Q quadratic, Q cubic, different types of convergences if I have a coefficient rho there. But again, if I start with a converging sequence, as long as this relationship holds, for any m can be any number, as long as rho is 2, 3, whatever. Then we have a cubically, quadratically converging sequence. As before, the speed of convergence depends on, should have been rho, on rho and on m, and they might depend on the algorithm and some other properties of the problem. We will see examples of this as we analyze different algorithms. And a quadratically convergent sequence eventually always converge faster than a linear converging sequence. In the end, they catch up and they will be faster. Examples are just to have in mind, these two sequences. This one is just the superlinear convergence, converging algorithm sequence, and this other one is Q quadratically. You can do the tests. There is nothing complicated about the test. But first, you have to show that they converge. Again, that's not hard. And second, we could use that statement because they converge. Then you can just construct that test. Okay, that was Q convergence. We can have its close relative R convergence as well. R convergence is, stands with roots. It comes from, it has its origin there. We don't need to worry about it. Really, the idea of R convergence, you can think of, instead of root, you can think of it as relative convergence. So if I have a sequence that behaves, I don't make sense of it, if I can find another sequence that bounds it, and that sequence that is bounding it behaves in a nice way, my original sequence inherits the convergence properties of that bounding sequence. So if the bounding sequence was converging linearly, then I can call my original sequence R linearly convergent. If the bounding sequence was converging quadratically, I can call my sequence R quadratically converging, a converging sequence. Okay? If anyone has anyone done any nonlinear dynamics analysis? So it is really the definition of, you can use it as Lyapunov stability for discrete time systems. That's exactly how we treated those.
Say often resolves? Doesn't it always resolve?
No. There are certain scenarios that they don't map back and forth. Just an example here is a sequence like that. if I bound it by this sequence, it is Q linearly converging. If a sequence is, R linear, if a sequence is R linearly converging, it might be, its rate of convergence might be in fact faster, but we don't have any certificate for it. We cannot make any statement. This just gives us some general guideline. If something is Q quadratically converging, it is R quadratically converging as well, because I can use the same sequence as its own bounding sequence. The definitions hold. But then the relationship only goes there. If something is R linearly converging, I cannot conclude it being, I don't know, Q superlinearly converging. All right. Some very basic stuff here. The idea of a bounded set, open set, and closed set. A bounded set is a set such that I can find some number that the elements of the norm of the elements of that particular set are bounded above by that number. So that's a bounded set. Definitions of open set is, okay, I need an object like this. I call it a ball. It's a norm ball, exactly. So if it is a Euclidean norm, it is some hypersphere. I call a set open such that if I pick any element of that particular set, I can always find some radius for my ball that the whole ball remains inside set F. Doesn't matter how small that radius is, it always exists. And then we do have definition of a closed set. A closed set is a set that if all the sequences of points in this set F, their limit points are elements of F as well. So really, if I have a sequence that remains inside set F, if it has any limit points, the limit point should be inside set F as well. It doesn't converge to anything outside. Now, a question. Is it true to conclude that openness of a set if it's not closed? So if I have a set that is not closed, can I conclude that is open? Yes or no? Who says yes? Who says no? Okay, Mark, why yes? So the statement was, a set is not closed. Then can I say it definitely is open? Let's think about an example. Imagine is this set, it's an interval, is it closed? Sorry, what? No, it's a binary question. Is it closed or not? No. Is it open? Okay. The definition of open set was if I can find, for any element of the set, I can find a sphere around it, a ball around it. So let's pick the element B. Can I fit a ball around B such that that ball remains inside the interval? No, right? because anything, even any variation to the B on the right-hand side, let's say, drops out of the set. So this set is not open. It's not closed either, because I can find a sequence that converges to A, but A doesn't belong to the set. So closeness and openness, they are not mutually exclusive. I can have these in-between sets. Then I can construct interior and closure. Again, they have precise definition. Interior of a set is the largest open set inside F. And then the closure is the largest closed set that contains F. So you can think of it as, there are terrible use of words, but you can think of them as inner approximation and outer approximation of the set F. So we squeeze it as much as we can, it remains closed, that's the closure. We blow it up as much as we can, as long as it remains open, and that's the interior. So for example, if I have a set that doesn't have its boundaries, its closure is the set and its boundary. If F is open, then the interior is the same as itself. And if F is closed, its closure is the same as itself. The union of finitely many closed sets is closed. And finitely many, that's the key. And the intersection of any closed sets, finitely many or infinitely many, remains closed. We have the flip of it for the open sets. Intersection of finitely many open sets is open, and any union of open sets is open as well. We need a definition for neighborhood. The neighborhood is, we call N a neighborhood of X if it's first open that contains X. And that's it. Now, as an example, something that is always handy to pick as a neighborhood, an open ball with some radius epsilon centered at X is a neighborhood of X. We can have the neighborhood of a set F as well. If given a set, we call N to be a neighborhood of F. If I can fit all the balls around the members of F to be inside N. So I can have neighborhood of sets as well. Another important definition is the definition of compact sets. We call a set F compact if every sequence in F has at least one limit point. And all of them remain in F. Now in Euclidean spaces, if F is closed and bounded, it is compact. Go and check the definitions that we use, why it's the case. For example, in this setup, this is not compact because it's not closed. This is compact because it's closed and bounded. This guy is not compact. Even though it is closed, it's not bounded. All right. Weierstrass has 3 theorems that underpin everything. This is one of them that we use as well. This is the first theorem that you will see. The second, technically, but yeah. the idea is this. If I have some set X, calligraphic X, which is non-empty and compact, so but in our case, we really say bounded and closed. If F is continuous, then a global minimizer exists for this problem. The proof, a version of the proof, sketch of the proof, follows these 3 steps. We define the graph of some function f. It's really what it is. Given all the elements of set calligraphic X, let's put the value of the function as the last coordinate, so we've lifted things in a higher dimensional space. So we construct a graph. That's the definition of a graph of function. G is a compact set because the assumption was X is bounded and closed. F is continuous as well, so it doesn't suddenly become unbounded. So G is a compact set. And if it's an idea of a projection. Projection of G onto its last coordinate, so it just chop all the starting points and only keep the last element. This remains compact as well. And now because it is compact, it means it's closed and bounded. So it has a minimum and a maximum with everything in between. Thus, because it's closed, there was a point that corresponded to that lower value for the value of the function. Now, it's a theorem which is, well, might help us characterize a solution and check if such a solution exists. It is useless in terms of constructing methods. Because it's really, to be able to construct a method using this theorem, it means we have to go and evaluate the value of the function for every single point. And that was the whole point that we were talking about. It doesn't make any sense. So, this is a sort of existence theorem. We see a lot of them. It really allows us to answer a very simple question. If I ask a question, is there a solution to this problem or not? These sort of theorems help us with these type of questions. They don't help us with constructing that solution. So that's the other things we need to be able to construct solutions. Now, there are definitions for different types of minimizers. There are three types. We have a local minimizer, we have a strict local minimizer, and then we have an isolated local minimizer. These really help us. You have to, when you see these definitions, you have to look at them from the perspective of, as a practice, to read these definitions carefully, because they're slightly different, every single one of them. Let's look at the first one. So we call some X star to be a local minimizer if I can find a neighborhood n of that X star such that the value of the function for all the points in that neighborhood is larger than or equal to value of the function at X star. So I find the point X star, I test things around it. If all the other values are larger, then I'm at a local minimum. It's local because we're only testing a neighborhood. The neighborhood can be large, small, but it's a neighborhood nonetheless. Then we have the idea of the strict local minimizer. We call X star a strict local minimizer if, again, we have a neighborhood and the value of the function is strictly less than everything else in its vicinity. The other one had less than or equal. Here it is strictly less than that. Okay? And then we have the isolated local minimizer is a vector x star such that if I find the neighborhood of x star is the only local minimizer. Okay? So these are the three definitions. Let me ask a question. Is any strict local minimizer a local minimizer? Yes. It's not a trick question. Yes. Because if this holds, it will hold with equality as well. And then the definitions match. Is any strict minimizer an isolated local minimizer? Yes, because there is nothing else that can be defined locally as a minimum. Good. Now, the trick question is here. Is any isolated local minimizer, the other one. Is any strict local minimizer, hang on, I tricked myself. Not every strict local minimizer is an isolated local minimizer. Can you construct a counter example? Yeah. My favorite counter example, maybe, I don't know. We need this. No, next slide. So let's consider this. So let's assume a function that looks like this. Everywhere it's 1, then it has a hole there, and there it's 0. This guy is a local minimizer, and it's a strict local minimizer, right? Strictly, its value of the function there is less than everything else in its vicinity. But is it isolated? No, because if I pick any neighborhood, in that neighborhood there exists a point here, which that point there is a local minimum itself, because I can find another neighborhood around it, which everything else, the value of the function is the same there, but yeah, doesn't matter. It fits the definition.
So neighbourhoods don't have to be the same.
Sorry?
The neighbourhoods don't have to be the same in testing
No.
cases.
No. Because the first neighborhood, I'm testing it for this, but then the definition, to test if it's a local minimum, I have to find another neighborhood. So they don't need to be the same. Now just some schematics. This is a local minimum. This is an isolated local minimum. These ones, they might be next to each other. It can be a flat surface. And then we can have the global minimizers. If I pick my neighborhood to be the whole set X that I'm looking at, just grow it so that it covers the whole space. Now this is the most important one of the most useful theorems, full stop. Taylor's theorem. You can think of it as it's a mean value theorem and fundamental theorem of calculus combined. It's pretty good. We use it heaps. In your first homework, you have to go and prove these sort of statements. I mean, what it really means is think about proving the statement because it really helps you refresh your memory. Or be lazy and go and copy it from somewhere, but then you will not learn. Again, I don't care if you copy. I'm treating you as grown-ups. Pick the thing that is good for you, because it seems you're going to have an exam. You have to be able to, and the exam will be open book as well. So you have to be able to show understanding. Copying would not be enough. Anyways, so these are the statements, the Taylor statement, Taylor's theorem statement. What it really, the first statement is the value of function at some perturb value of x, if I'm at point x, so if I perturb this point x by p, I can write the value of function at x plus p as the value of function at point x plus some term that is the inner product of my perturbation and the derivative of the function f in the neighborhood of x. So I can always write it like this. And then I can have the second order version of the approximation as well. I can write it as the value of f, the inner product of gradient and the perturbation, and some version of the Hessian. Again, that would be the first, one of the questions in the first homework. Now, how do we use it? We have the first useful theorem that you've seen before, probably in high school. I don't know, different people come from different backgrounds and education, but that's what it is. We call it the first order necessary optimality condition. It has a funny sounding acronym as well, but yeah. It says, suppose that x star is the local minimizer of some function f, and we are assuming that the f is differentiable, so these objects make sense. Then the gradient of f vanishes at x star. The gradient is equal to 0 at x star. Okay. Now it's a necessary condition. What does it mean? So, if I can find some x bar where the value of the gradient vanishes at x bar, can I conclude that it is a minimizer? Who says yes? Who says no? Can someone tell me why not?
Intersection point is a gradient theorem.
Yeah, okay. That's an example of a condition, a situation that this doesn't hold. So if it is a minimizer, then definitely it has to satisfy this condition. If it satisfies this condition, it doesn't mean it is a minimizer. Okay? Now let's see how we can prove it. There are different, again, ways of proving it. We use proof by contradiction. It's called ad absurdum proof as well. And the machinery relies on the fact that we assume what we want to show doesn't hold, and we work our way until we get something that is categorically wrong. So we end up with an absurd conclusion. So then, because of the chain of reasoning, we have to go to the beginning, then the original statement should have been negated. Okay? I am sure that not all of you are very comfortable with mathematical proofs. That's why on LMS, I've put a bunch of resources that talks about logic and proofs. Go and look them up. There are lectures as well that you just put the. It is important to refresh your memory. If you've done any class on geometry, Euclidean geometry, probably you are fine, because that's all of these things come out of that, the machinery at least. Anyways, we are going to obtain a contradiction. So we assume the gradient of f at point x star is not equal to 0. That's something we want to prove. We wager it. We say, okay, let's assume it's not true. Then we can define p as the negative of this value of the gradient of x star. Then the inner product is less than 0. Why is that? Because p is minus grad of f at point x star what is the inner product of a vector by itself? It's Euclidean norm squared. What is the sign of the Euclidean norm squared? It's positive. Because of the negative sign, it's definitely less than 0. Why is it strictly less than 0? Because this. A norm is only 0 when the vector is 0. Okay, so far so good. Now, we know the grad is continuous in x star because f is differentiable in the vicinity of x star. Then I can find some little perturbation around point x. It's really a continuity statement that the sign remains negative. And then we apply the Taylor's theorem, the first statement of the Taylor's theorem. We approximate it in the vicinity of these perturbations from this t, because it's in this neighborhood. There's another theta between 0 and 1 here. So this term was negative from this argument, so I had fx star plus some negative term. If I have a number, add a negative term to it, it is less than the original number. So now I ended up with a local perturbation that gave me a smaller value for the cost function. It is absurd. Why is that? Yes, because we started with that assumption. So we wanted to prove something, we wagered what we wanted to prove to be wrong, we showed that it is impossible. That's the proof by contradiction. Hardy has a good poetic description of proof by contradiction, which I can't remember, but look it up, it's pretty good. All right. Now we can have a second order necessary condition as well. Again, it's necessary. We suppose x star is the local minimizer, and f is twice differentiable, so it has both a Hessian and a gradient. And then we say, then the gradient should vanish. It's the previous condition that we showed. And additionally, the Hessian is positive semi-definite. So for a general function f with x being a vector, what sort of object is the Hessian of f? Okay. What is the gradient of f if x is a vector? Is it a vector or is it a scalar? It's a vector. Look up your calculus books. I'm serious. Now, what is the Hessian? Is it a vector or scalar or a matrix? It's a matrix. Again, look up your calculus books. the simplest way of thinking about it is if you just use the tools, it's just a Jacobian, right? All right. Now, what does it mean if I say a matrix is positive semi-definite? No, not determinate. The eigenvalues are positive. They are non-negative. Why can I say eigenvalues are non-negative? Because eigenvalues are not generally real numbers. Why can I say that here? Spectral decomposition theorem. The eigenvalues of symmetric matrices are real. A Hessian is a symmetric matrix. Hermitian matrix, really. Yeah, they are real. Now, if I again said a bunch of things that didn't make any sense to you, you have forgotten them. There is no linear algebra course in the history of mankind that doesn't cover these. You might have forgotten them, but we really need to brush them up again. We will review some of these things next lecture as well. There's another way of defining positive semi-definite matrices. It's like if I'm given a matrix, I hit it from the left with a row vector, and the transpose of that row vector from the right, for all possible choices of these vectors, the result should be, if it is non-negative, the matrix is positive semi-definite. Okay? Yeah?
Why we find the neighborhood is open?
That's the definition of a neighborhood.
All the theory is open neighborhood. Could we use that?
We have to change the definition, yes, but if you talk about closed neighborhoods, I am sweeping stuff under the carpet here. I don't get into details. Then we have to be more careful when we invoke the Taylor's theorem. So invoking things in open neighborhoods makes things easier. Now again, in this scenario, we are going to do proof by contradiction. We assume the Hessian is non-positive definite. We follow the same thing. We say, okay, there is a P such that this thing is negative because that's the definition of non-negative, non-positive semi-definite matrices. There is a direction that if I hit it from the left and right, the result would be negative. Because these things are continuous, then there is a neighborhood around. I can find some little tau in this neighborhood 0 and t, such that all these Hessians in that vicinity end up being negative when they are hit left and right by p. And then we invoke the second Taylor's statement. The value of the function of the perturb value of x star by perturbation tp is fx star, plus this guy, this is set to be 0, so it goes away, plus this other guy, which is less than 0, now end up being fx star. Again, it's a contradiction with the original assumption. Both of these conditions are necessary conditions. They have a corresponding sufficient condition as well. Now, the sufficiency states like this. If I can find an x star such that the gradient vanishes at x star and the Hessian is strictly positive definite, then x star is an isolated local minimizer of f star. What is the difference between this statement and the previous statement? The previous statement said, if x star is a local minimizer, then the gradient vanishes and the Hessian is positive semi-definite. So the eigenvalues are either 0 or positive. This statement says, if I find some point x star, evaluate the gradient and it vanishes, and then evaluate the Hessian, and its eigenvalues are strictly positive, then that point is a local minimum. So the gap between necessity and sufficiency is just one equality. Okay? We can prove this by a constructive proof. So we have to go both ways. Yeah. Sorry, it's only one way. All right. If the Hessian is continuous in the vicinity of x star, which is the assumption, and it is strictly positive, then I can always find some ball that the value of the Hessian remains positive. Again, locally, the properties don't change too much. That's a consequence of continuity. Now, for any point inside that radius, if I perturb the value and I invoke the Taylor's theorem, this guy vanishes, I end up with a value of a function that is larger than fx star. So if I'm here, it's fx star plus this term. So in any direction that I go, I'm going to increase the value of the function. Then that's the definition of a local minimizer, strict local minimizer. One thing that is important, like all the other sufficient conditions, if I have a point that doesn't satisfy the test, it doesn't mean it's not a minimizer. Any sufficient condition is sufficient. So if something doesn't satisfy that condition, it doesn't mean we don't have the property. It only means our test was inconclusive. An example is this. For example, function x, a quartic function in x, we know the minimum is at x equal to 0, but if I evaluate the Hessian there, it is 0. So it doesn't satisfy the test, the sufficiency test. Okay? So we have to be careful when we use the sufficient conditions. Necessary conditions allows us to discard candidates. If they don't satisfy the conditions, they are definitely not the solutions. Sufficient conditions allow us to verify candidates. If they satisfy those conditions, we know they are the answer. But if they don't satisfy the conditions, we don't know. It's inconclusive. That's any of these necessary sufficiency conditions are like this. You have to treat them with a bit of a care. We have one more minute. And we might as well just quickly, I tell you one quick thing there, then we call it a day. There is a tendency to treat multi-objective optimization problems as a different category of optimization problems, but that is absolutely wrong. If you are going to solve a multi-objective optimization problem, we end up using all the theory of all the other methods. The way that we interpret the result will be different. Again, something that we will really see it in later on, but I just wanted you to be aware of it. Don't treat multi-objective optimization problems as a completely different type of problems. They really are the same. The way that we interpret the result